All right, next up we have Sam. Why don't you take it away, Sam?
All right, thank you. Hi, my name is Sam Stites, and today I'm going to talk to you about a multi-language approach to probabilistic program inference. So this is work with my advisor, Stephen Holtzen, at the Northeastern PRL. So there are a lot of probabilistic programming languages out there, and a natural question that sort of arises is, why are there so many? So it turns out that when you design a probabilistic programming language, there's a large design space that we have to account for. And when we have small additions to a language, we might have a huge impact on inference performance. There's this sort of informal expressivity tractability trade-off where we want to present users with better representation power for practical problems, but at the same time, the more we restrict a language, the stronger the guarantees are for faster inference. So let's take a look at one of these languages called Dice. So Dice is a newer language. It was introduced in UPSLA 2020. And it's very good at these kind of graph reachability problems, which we're going to sort of touch on right now. So in this setting, we have some start node, we have some end node, and we just want to model the probability that a packet is going to traverse some kind of router network. And we'll use a probabilistic routing protocol, which really just means that when we go to write this Dice code, we'll define some network, we'll model the first node as a Bernoulli distribution, and we'll basically just repeat this process for all of the nodes in the network. And there's a little determinism as well. And so Dice, as I mentioned, is really good at this. If you have complex discrete structure, like that's great. It can handle many variables, it can handle observed statements, it's fast. So if this is your requirement, then we're all good. You know, it uses knowledge compilation under the hood, and it's just a detail. But like, what if you want something just a little bit more practical, like uniform distributions, or like Poisson distributions, or like loops, or even real numbers? That would be nice. But Dice can't handle that. So let's take that graph reachability problem and make it a little bit more practical. Let's now ask the question, what if we want to model an unknown number of packets arriving at our destination? So a slight modification, we'll just take the same network code, put it off to the side, and we'll model some p number of packets traversing the network. We'll model that as Poisson. We'll loop over each packet, and each time we'll just call the network function and find out whether or not it traverses. So we'll just sum this up, and it'll round out the model. So that's great. But as I mentioned, Dice can't handle this, and that makes us sad cats. If we were to use some language like Pyro, then we would be clear. We would be in the clear. We can express this, no problem, but we would lose out on the benefits of tractable inference that Dice was providing, which also makes us sad cats. So what if we could unify these languages? What if we could just use Dice for that network code and get the benefits of knowledge compilation, and then use Pyro for the continuous distributions and flexible primitives? So I think that we can, and I think we should. And on top of that, I think we should do this for all languages. Let's use scalable inference, specialized inference, and scalable inference for the places where it's appropriate, and use expressive operators when we want them. Let's use the entire design space. So in this work, we produced the first probabilistic multi-language with different inference runtimes. We have an implementation, it works on interesting examples, and we have an in-progress proof of correctness. So you might think, this all seems a little familiar. I can already write code in a low-level language when I need something fast, and I can already call it from a high-level language, which is what most of us like to program in. And there's already a lot of interoperation happening. So it turns out that multi-language programs are already everywhere. You can see them through foreign function interfaces. There's like a growing body of research on gradually typed systems. And on top of that, there's also like compositional verification. And so in this original Matthews and Findler setting of multi-language semantics, you might take some purple language here, and you might want to have it interoperate with some orange language. And we just have this small addition to both grammars where we introduce these banana brackets, these boundary operators. And this is really where we have this is where we have threats to type soundness and semantic soundness. So this is really where the details are. So how do we preserve probabilistic semantics in this context? Well, let's take this purple language. Let's call it our exact language, which does knowledge compilation. We'll make it a full probabilistic programming language, and we'll have expressions in this language compile distributions. Our orange language will do approximate inference and importance sampling. We'll make it a language that compiles down to weighted values. So how do we design these boundaries? When we're looking at a Bernoulli distribution in our approximate language, what do? Well, our exact language produces distributions. So we'll have to lift a sample into a Dirac delta, and this should, satisfy the requirement. On the other side, we have this exact value, which is a distribution, and here we'll need to perform sampling. But something interesting happens because the exact language doesn't know how to sample. So we have to give this responsibility to the boundary. But is that all? It turns out that there's a little bit more nuance. When we have these two languages and we just append these banana brackets, these boundary expressions, we can, at any point in the program execution, call into the other language, which means we have to reason about these partial programs and free variables. So if we take this fragment here, which is defining some Bernoulli distribution in the exact language, and then sampling it twice and accessing these by reference, then we can't just say that the boundary will just sample, because there are conditional independent structures and control flow which might become inconsistent when we do this. So there has to be a little bit of bookkeeping on both sides, where in the approximate language, when we call something from the exact language, we need to make sure that those samples are consistent. While on the other side, if we are in the exact language, calling the approximate language, we need to make sure that we're constructing valid weights and maintaining them through the lifetime of the sampler. So this is pretty cool. We just got expressivity, we got specialized inference, but then there's a third thing that happens, which is that we produced another inference algorithm. Specifically, we produced a partially collapsed importance sampler. So this isn't just an idea. We have, a prototype which actually does this work, and these two tables are really just trying to show you that we always get that partially collapsed importance sampler, and that we get performance benefits on some certain classes of problems. Yeah, that's my talk. Thank you so much.